folks, Mr. Comer here again. My hair just keeps growing outwards, ever outwards, like a shrub. I have a shrub on my head. Anyways, I'm here to walk you through the lab assignment for today. I'm going to show you how to work on the program that we are using for it, and really it's not too long of an assignment, and I hope you give it a try because I think it's pretty fun, and it's the closest we can get to actually working with circuits given the situation that we're currently all in. Great, so let's get started. All right, so as you can see here, this is our lab screen. It's going to give us all the components that we need to essentially build our own circuit. Let's take a look at some of the tools and components that are available to us. Over on the left here, you can see the basic components. So here's a wire, which will transmit electricity. The battery, which remember provides the voltage pressure, provides that push that runs the actual circuit. We've got a couple of different resistors. We have light bulbs for one, which of course light up when energy goes through them. And we've got an actual resistor right here that of course will heat up a little bit as electricity goes through it. Now its purpose isn't to heat up. The purpose of a resistor is to step down the voltage in some way, which can be used for many different outcomes inside of a circuit. But for our purposes, it's just acting as a resistor, something that will step down the electricity. Okay, there are some more things than that. As you can notice over here, as you go down to the next page, it looks like there's just another battery, light bulb, and resistor. These are extremely high voltage ones right here. These are if you were trying to show really high voltage DC circuits. We're not doing that, so you don't need to worry about them. But if you want to play around with a few things, for instance, if you want to play around with fuses, which are things that break when a certain amount of current flows through them in order to prevent the circuit from burning out, or in the case of somebody who has accidentally short-circuited themselves into the electrical pulse in order to prevent a death or an injury, feel free to play around with the fuses if you'd like. Now, let's practice by building a very simple circuit and using some of the tools over here on our right to actually do the calculations for us. So I'm going to get a battery. This battery has a voltage of 9 volts. I'll keep it at 9 volts. Works for me. Let's take a wire and let's connect it away from the battery. Well, I'd like to power a light bulb from this battery. So let's grab a light bulb, run the wire connection. Now remember, we have to make sure that the electricity is flowing in a constant circuit, right? A few people will do something like this. They'll connect a wire. They'll connect both ends of the wire to the exact same output. It's a short circuit, okay? This is what a short circuit is. It's when you literally make the connection too short. There's no or little resistance inside of the circuit. The voltage flows very quickly and things tend to heat up, break, and blow out when that happens. Well, why isn't the light bulb lighting up? Well, because we've got the electricity pegged through the same point. This isn't actually moving through the light bulb, it's just moving through the wire. Let's cut this circuit so that we don't have that battery on fire anymore. And very good. We've got a light bulb, and we're going to connect it properly in circuit this time, and much better. We've got a battery. Electrons are flowing out of the battery through the light bulb and back into the battery. Now, if I told you this battery is 9 volts, and I told you that this light bulb was 10 ohms, you should be able to use Ohm's law, voltage is equal to current multiplied by resistance, to tell me how much voltage is passing through this light bulb, and to tell me what the current is. But if we were actually in the lab right now, what I would do is show you how to use these two devices on the left. I'm going to show you how to use them in our little fake lab setup here. This is a voltmeter, and this is an ammeter. Dr. Samara talked a little bit about these in the video. Now, the way a voltmeter works and the way an ammeter works are very different from one another. Let's take a look at the ammeter first to judge current. In order to figure out what the current is passing through this simple series circuit, we have to break the connection and put our ammeter inside the connection, right here. Now, it tells us correctly that the amount of current, amperage, flowing through this circuit is 0.9 amps, and that makes sense. Again, if we want to find out current, V equals IR, we're looking for I, well then we divide both sides by R. So the voltage, which is 9, divided by the resistance, which is 10, equals 0.9. Great. Why is the ammeter connected in series like this? Well, remember, in a series circuit, current doesn't change, no matter how many light bulbs or resistors you have in a row. Voltage does for every single one, and I'll demonstrate that in a second with 2 light bulbs. So since current doesn't change, we have to literally go into the circuit with our ammeter, break the circuit, and make the circuit flow through our ammeter in order to determine the current. An ammeter has an extremely small amount of resistance, and because of this, everything flows through. It doesn't really affect the amount of voltage because the resistance is so small, and the device is able to tell us how much the current is. Okay, let's break the circuit, take away our ammeter. Before we reconnect it though, let's put in another light bulb. Now, you can see that these light bulbs are getting less energy than it was when it was just the one. Why is that? Well, it's because, again, in a series circuit, like we've seen in the videos that Dr. Samara has done and that I've done on our paper circuits, when we have a series circuit, voltage steps down across resistors and current stays the same. So if I break this and once again insert our ammeter, like so, you're going to see that the current has changed. And the reason why is because the amount of voltage has changed inside this series circuit, which means that our numbers are going to be different. Let's try this by trying our voltmeter. So I'm going to reconnect the circuit like so, and use our voltmeter now. Now the voltmeter works very differently from the ammeter. You do not break the circuit in order to work a voltmeter. This is because in a parallel circuit, which is what we formed right here, right? This is the series circuit, but the parallel connection is through our voltmeter. In a parallel connection, current is the one that changes, and voltage will be the same. So whatever voltage is passing through this part right here, the second light bulb, because there's a parallel circuit connected there, it must be the same amount of voltage passing through the voltmeter. Now voltmeters have an extremely high amount of resistance, so that they, again, don't really change much of what's going on inside the circuit, but allow us to correctly see how much voltage is flowing through. Again, this is something that we would be able to calculate on our own. If this battery has 9 volts flowing through it, and we've got 2 light bulbs, both light bulbs have the same resistance, 10 ohms and 10 ohms, well, 9 divided by 10 is 0.9, but because there's 2 of them, it's 9 divided by 20. 9 divided by 20 is 0.45. There's the current that we measured earlier, 0.45 amps, and if there's 9 volts and 2 light bulbs of the exact same resistance, well, that 9 has to be stepped down across both of them equally, 4.5 and 4.5. If we move our voltmeter right here to the other side, we'll see that the full 9 is flowing across the 2 light bulbs, but one of them is getting 4.5 and the other one is getting 4. Okay, sorry for the quick cut there. I just started hacking my lungs out, and I decided that you probably didn't need to hear Mr. Comer coughing for 5 minutes. Anyways, here's a quick show of what a parallel design of a circuit would look like. So as you can see right here, I've already set up a series one. It's pretty straightforward. Again, we've got a 10 ohm bulb. We've got a 9 volt battery. I'm going to take a wire and connect them in the middle. And I'm going to connect a new 10 ohm bulb to this. And again, I want you to keep a careful eye on the power output of this light bulb down here. The simulation will show longer lines for a light bulb that has more voltage and shorter lines for a light bulb that has less voltage. Let me connect it like so. And look at that. You probably noticed there wasn't any decrease down here of the light being output by this bulb when this one turned on. Remember, in parallel, voltage splits equally. If 9 volts are coming out of this battery, which they are, then that means 9 volts are going down this path and 9 volts are going down this path. What has changed is that the current has stepped up in response to this. And we can see this if we take our ammeter and connect it to our outputs, like so. So first, I'm going to connect it so that everything is flowing through it. Look at that, 1.8 amps. Well, we can decide then that what's probably happening is 0.9 is going through one arm of the parallel circuit and 0.9 is going through the other. And sure enough, if I remove my ammeter and I reconnect the circuit so that we just look at what's going through here, I'm going to click and then cut, great, and insert this one, 0.9 amps is shown, okay? So this is a parallel circuit design, one in which the current steps up to change, voltage splits equally between the two parts, versus a series current in which the voltage steps down and the current stays the same throughout, okay? What I want to have you do is create your own circuit. But I want you to follow these specific guidelines, and I'm going to write these on the actual assignment so you don't have to jot them down as I'm saying them. But let me walk you through them. I want you to have a combination circuit. What that means is you must have a series and a parallel. So for instance, if I wanted to turn this circuit that I have in front of me right now into a combination circuit, it's currently just a parallel, I'd have to add another light bulb onto one of these lines so that there were 2 light bulbs on one and 1 light bulb on the other. That would form a combination circuit because there's series light bulbs and parallel connection as well. Combination. I want you to have a battery. I want you to set the battery to 12 volts. You can do this by clicking on your battery like so and increasing or decreasing the voltage. So I can increase this, for instance, to 12 volts. Nice and easy. I want you to have 2 light bulbs. The first light bulb should have 10 ohms. The other light bulb should only have 5. Again, you can get this by clicking on the light bulb and decreasing the resistance. Finally, I want you to add a resistor, and the resistor should have a resistance of 12 ohms. One more time, that's a combination circuit with a battery with 12 volts, a light bulb with 10 ohms, a light bulb with 5 ohms, and a resistor with 12 ohms. Finally, I want you to tell me how much voltage and how much current is flowing through each one of these resistors. The light bulbs are a resistor. They're taking electricity and turning that resistance into light. So I need you to tell me how much current is flowing through your 10 ohm light bulb and how much voltage, how much current and voltage is flowing through your 5 ohm light bulb, and finally how much current and voltage is flowing through your resistor that's 12 ohms. Do you have to do calculations? Yes, you can, but you don't have to, because remember, this is a lab, and in this lab we have some tools available, the voltmeter and ammeter that I showed you earlier. You can use these tools to determine the voltage and current flowing across each part of your circuit. If you prefer to run the calculations, you're certainly welcome to. The only equation that you would need is Ohm's law, which is that voltage is equal to current multiplied by resistance. Whether you decide to do the calculations yourself, or whether you decide to use the tools here, doesn't matter, as long as you provide the correct numbers to me. How should you provide the circuit to me? You have one of 2 options. Option 1 is you can build your circuit here in this lab and hit the print screen button on your computer. When you hit the print screen button, now some of you on laptops might have to hit function print screen, but regardless, it takes a screenshot of what you're currently seeing. You can then post that into an email, or preferably what I'm going to set up is a submission form that you can post that screenshot into, and then you can send it right to me with the numbers that you've calculated or the numbers that you found with your tools. You've also got another option. If you don't want to just do a screenshot, if you'd prefer to actually draw out your circuit, then you're welcome to. Grab a piece of paper or use Bitmap on your computer if you want. Draw out the circuit using the circuit symbols that we've used before, the squiggly line for the resistor, the short line and the long line for the battery. You've seen them on my previous video, and you're welcome to watch that again if you need a rehash. But you can draw out the circuit and again, send it to me with the submission form. That can either be taking a picture with your phone or scanning it with your scanner in your house. How you get the form to me doesn't matter too much. You've got a lot of options on how to do this. And as long as you do that and give me the numbers, you get credit. One more thing, just because I get a kick out of it, and you electrical interested folks might get a kick as well, I'm going to drag out one of the resistors right here. You can see the resistor right there, right? What are these bands on the resistor, you might say, Mr. Comer? Well, electrical engineers have for a very long time developed a system that allows them to, at a glance, calculate what the resistance inside of a resistor is. And they do this using color-coded bands. I'm going to click on this resistor right here. You can see that I can change the resistance. I'm going to close my eyes. Let me just make sure I'm clicking on the right thing. I am. And I'm going to change the resistance. I'm just going to randomize it. I'm going to go up and down, up and down, up and down, up and down. Okay, I'm going to let go. I'm going to click away. Okay, so this resistor has a white line, a green line, a black line, and a gold line. What does that mean? You probably know because you saw the resistor down the bottom there. I'm going to bring up the 4-band codes. These are the codes that are used by electrical engineers. And I'm going to take a look at them. Well, if the first band is white, that means a 9. If the second band is green, that means a 5. And if the third band is black, that means a 0. So we've got 950. Is that 950 ohms? Not quite, because some resistors are very small and some resistors are very big. So how can you determine the amount of ohms when you could have something that might have 3 decimal places? Well, we do multiplication. So as you can see right here, this is the multiplier. If the final band is black, you multiply it by 1. Your number would be correct. So if this final band was black right here, this would be 950 ohms. But it's not, it's gold. Gold means multiply it by 0.1. 950 times 0.1. This must be a 95 ohm resistor. Let's click on it. I was right. 95.5 ohm resistor. Okay, I was close. I think maybe they left the 0.5 out. Well, in any case, that's how resistor bands work. I think they're kind of fun. And so we come to the end, at least for our seniors. Seniors, this is your final assignment before the end of the year. Next week, I know you're going to be heading into the school, doing your sign-outs, passing in your books. Please pass in your physics books. I'll come for you if you don't pass in your physics books. Anyways, you'll be doing sign-out. It's a busy week. I won't be assigning anything for seniors next week. If you haven't completed enough parts of the assignments that I've done so far in order to receive credit, please do so next week. It's just silly not to get credit considering what we've had to do this year. Okay, so please make sure you finish up. Use next week if you have to. Remember to reach out to me if you need help, or if you've had any problems at home that I can help you out with in any way by maybe changing what you need to do. Please reach out before you just throw your hands up in the air and say no. Juniors, there'll be one assignment next week. I'm also going to cut you a bit of slack because I know a lot of you are doing APs, and APs sound like they've been pretty crazy this year with the internet changeover. So again, next week, try and catch up on any work that you've left behind. All right, before we go, I would like to say thank you to some of the staff that have helped me making these videos. Here, of course, is PanCat. A couple of you called him Pen Cat when he gave the scar. No, he's Pan Cat. The reason why he's Pan Cat is because he has the Pan flag on his belly. Okay, so hi Pan Cat. I hope you're very well. We've also got one of my favorites, Lima the Llama, a gift from a student. She went to Peru to visit some family, and I told her, bring me back a llama. She nodded and said, I will. And she really did bring me back a llama. I wasn't expecting that. Anyways, here's Bolshevik. He's a wooden toy that my wife got me. He is a tiny Bolshevik soldier, and when you put him on surfaces, he walks. He's delightful. I get a kick out of him. That's when I was teaching history. Finally, we've got one of my favorites, the rainbow jumping spider. If you've never seen a rainbow jumping spider, I highly recommend you look up a video. This specific one is a Martus robinsoni. They are delightful little creatures that do funny dances with their butts when they see another rainbow jumping spider. Jumping spiders are incredibly intelligent creatures. I am big fans of them in all of their wondrous majesty. Fun fact about jumping spiders, that one eye is slightly larger than the other eye, which allows them to see parallax, much like we do, but specifically allows them to judge parallax. So if you've ever wondered, Mr. Comer, why do I need to learn things like Pythagoras' theorem and all this geometry? Well, it's because when a jumping spider finds its prey, it uses, essentially, Pythagoras' theorem to determine exactly how far away from its prey it is, so it can know exactly how hard it must jump to land on it. So you should learn math if for no other reason than a spider shouldn't be smarter than you. Have a good one, everybody.